Good morning, everyone. I'm Jian. I'm the senior microscopist and imaging analyst here at Monash Microimaging. I'm coming to you today from the land of the Wurundjeri people and the Bunurong people from the Kulin Nation, and I will take this opportunity to pay my respect to the traditional custodians and of the lands and waters on which Monash University stands. We are very fortunate today to have Professor Laura Waller present at our Monash Advanced Microscopy webinar. Laura is the head of the Computational Imaging Lab at UC Berkeley. Her lab develops methods for designing imaging systems and algorithms, including new generation cameras that integrates computers as a part of the imaging system. The optical setup and post-processing algorithms are designed simultaneously. And so you could, for example, digitally refocus your image or enhance the resolution. Their expertise extends to a wide range of imaging approaches from optical microscopy, EM, and X-ray. So before joining Berkeley in 2012, Laura did her undergraduate and graduate studies at MIT in electrical engineering and computer science, receiving her PhD in 2010. She then moved to Princeton University as a postdoctoral fellow and lecturer in physics until 2012. And she now holds the Ted Van Derzer Endowed Professorship and is a senior fellow at Berkeley Institute of Data Sciences. Her innovative and cutting-edge research has earned her the respect in her field. She is a Chan Zuckerberg BioHub investigator, an SPI Early Career Achievement Awardee, and a Packard Fellow. I will recommend you check out her lab's website. First, it's great to see her team grow over the years and her small children also grow. And there are some awesome videos of microscopy and of their research. So Laura's talk today is titled Computational Microscopy with Dynamic Samples. Thank you, Laura.
Thanks. Okay, great. Thank you. Hopefully you can hear me okay, and all the videos will play across the oceans. So I'm going to talk about a bunch of work in our group from a long time ago until very recently. And it's all related under this realm of computational microscopy. I'll talk about both 3D and phase imaging and fluorescence imaging with super resolution at the end. And the dynamic samples part you'll see really towards the very end. So computational imaging is this idea, it's a design philosophy in which you design your imaging system in terms of both the hardware and the software together. So some things are better done by optics and some things are better done in the computer. But it's fundamentally very different than regular imaging because you don't design your optics to get the best image and then design your post-processing to extract information from those best images you could capture. You rather design these two things together so that what you capture might look nothing like your final result, but you can reconstruct higher dimensional information or higher resolution or some sort of like better imaging capabilities. The new frontier in computational imaging is this idea of data-driven design, where we use the phenomenal tools of machine learning to search for like needle in a haystack type solutions to optimization problems so that we can design the imaging system hardware in conjunction with the software. And that's really cool because until now, the optical engineering piece of the computational imaging was always the black magic of expertise in
excuse me, Laura.
Optical engineering.
I think we can't see your slides. I don't know if you're sharing you have slides at the moment or not.
Oh, yeah, that's very weird.
I can't see.
You can't. Oh, yeah, I didn't share. Good point.
Thank you.
Yeah, okay. Sorry about that. I thought I had been sharing already. So now I think you can see. Let's see.
Yep, all good.
Except it's not switching. Okay, now you see the title slide. Great. Okay, yeah, so this is the idea of computational imaging and data-driven design that I was talking about, but you couldn't see. I don't have the green box. Can you still see this like hardware computational toolboxes?
Yes.
Oh, okay, good. I just don't see this green box. Okay, anyways. So a lot of what we do is phase imaging, quantitative phase imaging. And phase information is fundamentally computational imaging because phase is the complex part of the complex field. So X is like your object complex field. It has an amplitude and a phase. And the measurements we take are intensity, almost always with a regular sensor. So that's just absolute value squared on the complex field. So you lose the phase information, and you need some sort of this A matrix here, some sort of system matrix or some sort of like system forward model that will bring the phase information into intensity. Zernike won a Nobel Prize for this a long time ago. But nowadays, what we can do is quantitative phase, not just phase contrast. And so if you think about like, why is it necessary for biology? Well, cells are largely like bags of water floating in water. They're pretty closely index matched, and so they don't absorb a lot of light, but they might like scatter light, or the phase can get delayed. So if you don't stain or tag your cells, you don't see them very well. They're pretty transparent. But if you can measure the quantitative phase information about the cell, then you can get a map of the morphology and density, which in this case is quantitative in the sense that it actually maps to physical quantities. So phase contrast, like Zernike phase contrast, is very useful because you can see things that are purely phase changes that don't, if your sample is not absorbing a lot. But quantitative phase gives you a whole new dimension to be able to actually map this to physical quantities. And you'll see later that that leads to looking at 3D refractive index measurements. So I spent a lot of my career on different ways to measure quantitative phase in microscopes for biology. I've done a lot of different ways through focus, etc. But one of the best ways I've seen, and it's started from Jianhui Yang's group at Caltech, is this LED array microscope. So you take off the illumination unit of a regular bright field microscope and you replace it with this LED array. So this thing's like literally a toy. Adafruit's a toy company. It's controlled by an Arduino. At Berkeley, like most of our undergrads can program Arduinos. And so you can just turn on different LEDs in the array, and the array is just sitting above the sample. It's big. It's like 5 inches by 5 inches big. So it's this big LED array sitting above the sample. And basically, if I light up the central LED, then I'm illuminating the sample effectively with a plane wave on axis. By the time it hits the sample's in a small area. If I light up an LED over here, then it will illuminate the sample off axis with what's essentially a plane wave. And so we can model this as like patterning the illumination angles at the sample. So like, who cares? What I want to show you is from this simple, cheap hardware modification, we can do all kinds of different imaging modalities by treating this as a coded illumination problem. So we have computational illumination, and we're going to design which patterns to display on the LED array while we take a bunch of images, and then we have algorithms that can reconstruct the image to get different modalities. So like different contrast modalities. This is essentially super resolution imaging or 3D imaging. And I'll explain each of these. So the easiest to explain is like if I just turn on the center LEDs, this is basically just a bright field microscope, right? But notice that I have like a circle of LEDs here. So that circle represents the illumination angles, the range of illumination angles that map to the illumination angle detection capabilities of your microscope objective. So if you have a high NA objective, you can collect high angles. So this circle would be bigger. So if I illuminate the sample with LEDs that are outside of that, what I call the bright field circle, or the circle inscribed by the NA or numerical aperture of the objective, then I'm illuminating with angles that are not capable of passing through the objective. And so what I'll see is a dark image unless the sample is scattering the light back into the aperture. So when you see stuff light up in this image, it's stuff that's scattered to angles beyond the NA of the microscope. And that's dark field imaging. And then taking it one step further, if I illuminate half of the LEDs in the bright field circle, I get this phase contrast image. So like phase information lights up. It's not quantitative phase information, but it's contrast set by the phase. It looks a lot like DIC, differential interference contrast microscopy. It's not exactly the same thing, but it's quite related. And we can time interleave the 3 of these so that we can get them all at once. So normally to get these 3 different images with these 3 different modalities, you'd have to switch out 3 different objectives and pay a lot of money and take a lot of time. And every time you change the magnification of the objective, you need to change your you need to put in a new objective. So like changing out hardware. But now I can do all of this simply by choosing which LEDs I turn on. If I change the objective to a different NA, I just change the size of the circle on the LED array where I'm lighting things up or not lighting things up. And in fact, we wanted to get to quantitative phase, and we came to this method of differential phase contrast. So you take the LED array and you light up a half circle, say the top half circle, and that gives you this phase contrast image. Some weird, like, it looks like a relief image of the cells. And then I take a second image where I light up the bottom half of the LEDs in that circle, and I get a different phase contrast image. And so if I add those two together, it's as if I had taken a bright field image. It's the same thing as if I had just lit up all those LEDs at once, and I lose all of my phase contrast. But if I subtract those two images and divide by average, then I get an image that we call the DPC image, or the differential phase contrast image. And this image is quantitatively related to phase. So if I take the first derivative of the phase, that's what this image essentially is. Really close to that. We model it a little bit more carefully. But then I can just take the inverse first derivative, just integrate, and I can get quantitative phase across the cell from just a couple of images. We actually take 3 or 4 images with different orientations of the circle just to fill in some gaps in the Fourier space. But then you can get really fast quantitative phase imaging. And these are some examples of like vesicle tracking and things that were moving in the cells that were like previously too fast to be seen by other methods that I had worked on previously. So I was really excited about this method. It has good fidelity. It's an incoherent microscopy method. So you get the full doubled diffraction limited resolution. You get the incoherent diffraction limit of resolution. And it's really stable type of phase imaging because you have partially coherent illumination. And it's cheap and simple to implement. You can do it simultaneously with fluorescence images, or you can time interleave with these dark field illumination methods so that you can get different contrast modalities pretty easily and all in one microscope. Okay, so that's like real-time multi-contrast. The coolest thing that this LED array microscope can do is this gigapixel imaging. It's all based on something called Fourier tachography. Some people probably heard of that. But the idea is to go after a huge field of view with also good resolution. So just like a camera, the microscope has to choose. You choose an objective, and if you have a big field of view, you're going to have bad resolution. If you zoom in and want good resolution, then you have to give up field of view in general. And that's actually fundamentally limited by aberrations and money. But the idea of Fourier tachography is to get both. So you can end up with like gigapixel scale images from a regular bright field microscope. And you sacrifice time to get it. So what you do is you start with a low NA, low magnification microscope that has a huge field of view, but it's not resolving the smallest features here. So it has poor resolution, but big field of view. Then you do this disco party patterning of your LED array to capture images with different illumination conditions. And what you see is like all of these images I capture are low resolution, but they're low resolution in a different way. Stuff is changing, which is good. And from that video, I can reconstruct, in this case, 7 times higher resolution in each dimension. In fact, my final resolution goes as the diffraction limit, lambda over 2NA. But instead of just using the NA of your microscope objective, you get to add the NA of the objective to the NA of the illumination. So that LED array, I think it had 0.6 NA. So you get to add that to whatever your native NA of your objective was. We now build domes of LEDs that go out to a full 0.98 NA. So you can basically add like +1 to your NA and get the diffraction limited resolution up to that for whatever field of view you have native to your objective. Okay, so how does this work? I have to go to Fourier space. Some people probably are afraid of Fourier transforms. That's fine. It'll be quick. But basically, you look at the Fourier transform of the samples. This is the spectral information, spatial spectral information of the sample. So UX is like spatial frequencies along X, UY is spatial frequencies along Y, and your microscope has a natively low NA, meaning that the bandwidth of spatial frequencies it captures is relatively small. So numerical aperture and spatial frequency are essentially interchangeable. Talking about angle, or like the angles, the angle of your numerical aperture sets the band limit of your system. It tells you what spatial frequency and angle are very similar. You can think of them conceptually the same idea. They just have a scaling factor. So if I illuminate from an on-axis LED, what I collect is all the stuff inside this green circle. I get a low resolution image because it has a small bandwidth. And then when I light up an LED outside, like a dark field LED way out here, then what happens is I collect a dark field image. So it lights up sub-resolution information about the sample, but the image itself is still low bandwidth. So that's to say, like, basically what you do is you shift the circle. So you come in at an angle, that's a phase ramp. In Fourier theory, that means it's a shift in Fourier space. So what you get is this circle shifts in Fourier space, and the image you collect actually contains these spatial frequencies. And so now you can kind of see like what's going to happen. If I light up an LED up here, I collect these spatial frequencies, all the horizontal edges, sub-resolution edges light up. And then if I were to go and collect a whole bunch of images, one for each LED, then each LED covers a different circle within this Fourier space. Then I can build out a much larger circle in Fourier space. This is called synthetic aperture. And this is the idea, is that you just build out this larger bandwidth in Fourier space. So a larger bandwidth of spatial frequencies is going to correspond to higher resolution of your image. There's a couple of caveats. So one is that we measure intensity, absolute value squared. And so we have to also solve for phase, because to like stitch all this stuff together in Fourier space, you need both amplitude and phase information. You need to do an inverse Fourier transform, which involves both amplitude and phase. And so we need to do phase retrieval plus synthetic aperture. And the phase retrieval is enabled by the fact that these circles are overlapping a lot. So that is an inefficiency per se, but it won't work without it. So you can't do the phase retrieval without it. So the way to solve for phase, so this is the complex field in Fourier space is what you're solving for. It's just a big optimization problem, nonlinear, non-convex, but it seems to work. There's a lot of past work on this. People have been doing this for a very long time in very different contexts. So it was relatively easy to dump this into an optimization inverse problem and solve it. So you're solving for the complex field in the Fourier space of this gigantic stitched together Fourier transform. We also solve for P of U, which is the pupil plane. This is basically like the wavefront aberrations in the pupil plane, because then we can digitally remove aberrations, and all of my images have aberrations digitally removed from them, like as a sort of like freebie joint solver. So how you solve that optimization definitely matters. The like typical way of doing it is this Gertrude-Saxton type approach. It's really easy and simple. It's a type of gradient descent. So Gertrude-Saxton is a subset of gradient descent, but it's a first order optimization method. You take the derivative of your loss function and then you update based on the derivative. So if you start to like eliminate or like reduce the overlap as much as possible, it starts to fail, you get weird artifacts. Second order optimization works way better from the same data set, but it's extremely slow. So we're looking for something that is fast enough, but accurate. This is my speed versus accuracy commentary. And the algorithm that we have that does that is this Gauss-Newton algorithm. It's called a quasi-second order optimization. Second order optimization uses the second order derivative, which is a gigantic matrix called a Hessian. And we just use we only compute the diagonals of the Hessian to keep the thing fast, but it seems to be pretty much just as accurate without all the extra calculations. So that gets us to being able to look at these big fields of view with high resolution and quantitative phase. So this is quantitative phase. The resolution we get is equivalent to that you would get with an ADX objective, but this is the field of view you would have gotten with that ADX objective, and now you have this much, much larger field of view. You can see this is HeLa cells. They curl up in a ball and then divide into a bunch. This one's dying. And when it curls up into a ball, it kind of like peels off the surface of the liquid and moves axially, but that's okay because we still have this big depth of field because we used a low NA objective to do all of this. You can segment all of this quantitative phase information when you've done it right. Okay, so then I get to the trade-off. So you get good resolution and good field of view, and the sacrifice is time. So you have to think about what samples you're looking at. If your sample is alive and moving, then you really have to think about this, right? Like, so if it's cell migration and division type stuff, like really slow type stuff, like the HeLa cells were pretty slow, you can take hundreds of measurements You can take like 100 different of those green circles to fill in a bigger Fourier space. But as the cells are moving faster and faster, you don't have time to take that many measurements. And so you run into this limit where you don't want all of the super resolution that you were going after to be lost due to motion blur because your sample's moving too quickly. Excuse me. So our solution to that was to look at this pupil overlap. So every time we turn on an LED, it collects one of these green circles. And the green circles are like overlapping by a lot. And I said we need that to get the phase retrieval to work. So you can't simply pull the circles further apart and take less data, but it amounts to collecting 10 times more data than we actually reconstructed. So I said we can get to like gigapixel scale reconstructions, but then we're like collecting like 10 gigapixel scale data sets to get there. And that just seems inefficient. So we wanted to get rid of that. You can't get rid of the overlap. So what we did was for the bright field LEDs, we did these half circle illuminations from the DPC. So you get twice as much resolution from just 3 images. That's a good deal. And then in the dark field, that doesn't work. So we just chose to like randomly sample the dark field, 8 LEDs at a time. So because we're turning on 8 LEDs at a time, that's what this disco party pattern was, then you can take an 8 times shorter exposure time, and you're filling in 8 different parts of the Fourier space with each image, sort of, hopefully, as long as the algorithm still converges. But it does for the factor of 8. So you can reduce your capture time for data by almost 2 orders of magnitude. Excuse me. Just by doing this multiplexing approach. So this was really valuable to get at fast sampling. But then we got more sophisticated. I said that machine learning is really taking over in computational imaging, and we're getting really good at this end-to-end learning, trying to optimize the hardware as well as the software. So then we had like the machine learning figure out the ideal LED source patterns. So if we take 1 LED at a time, we have 89 measurements. We get this result. If we just drop to 10 measurements, I didn't show it here, but you would just get worthless results from 1 LED at a time. But when we use this pattern of 10 different measurements taken with these LED array patterns, then we can still get a pretty good result with just 10 measurements. So we can get huge speed up factors by all of this kind of like optimizing the patterning. All right, so I showed you this Adafruit array. It was fun. It was a cute toy, but it wasn't very practical. You can't do multiplexing with it, so you can't turn on multiple LEDs at once. It doesn't actually turn them all on at once. It just like turns one on at a time in a really fast duty cycle that maybe your eye can't see, but our camera can, because we're trying to run the camera at like 100 frames per second. So then we started building these domes. We also wanted to improve the light efficiency at high angles. So at high angles, the flat LED array has like not very much light getting to the sample for lots of reasons. It actually, the LEDs are directional, it's further away, so the light is dropping off, and it's not like, and it's like not coming in like from an angle, so you also have Fresnel reflections. So we started pointing the LEDs properly at the sample in a dome shape, so they're all the same distance from the sample. This was the first 3D printed LED array dome. It was hand soldered every single LED. So Zach did that like within a few months of arriving at Berkeley, and then realized that he didn't want to do that anymore. So he started mass producing them on these printed circuit boards that we outsourced the manufacturing. And these things have like adapters they can click directly into the condenser unit of most bright field microscopes from big companies. So we have a small startup company that basically just buys these in bulk and sells them off one by one. So if somebody wants to try this kind of approach, you can get going really quickly and easily for not that much money. Okay, so the last piece of this that I want to get to, that's the biggest piece, is in 3D imaging. And this is the idea that as I'm illuminating from different angles, I told you that things are shifting around in Fourier space, but that's only true if your sample is thin. So if your sample is like thinner than the depth of field of the microscope, then you get these shifts in Fourier space when you illuminate from different directions. If your sample is thick, like 3D sample, then when you illuminate from different angles, it's more like tomography, you like project through the sample in different ways. So this is a sample that's 2 resolution targets, one above focus, one below focus. And as I shift my illumination direction, what happens? it looks like these things are walking across the screen in different directions. And the faster they walk across the screen, the further they were from focus for a given illumination angle change. The stuff in focus won't like walk across the screen with the illumination angle. So we're getting depth information here, right? How fast the thing is walking across the screen. So this sample is just to show that there is depth information there. So we need to extract it. We can. The algorithm's not actually that different. You just set it up as a big 3D algorithm, and you can solve for 3D quantitative phase of the sample. So the 3D quantitative phase of the sample isn't really a thing because phase is a projected quantity. And so 3D quantitative phase basically means 3D refractive index. So when I say phase is a projected quantity, it's like 2 pi by lambda refractive index difference times thickness. And so now you can separate those two out. And so this is a map of the 3D refractive index, and you've like isolated the thickness effects. These are mouse embryos, and you can see the 3D refractive index at different depth planes as I scan through the embryos. These are pretty early stage, so they're not too scattering. The algorithm can be talked about as if it were like a big neural network that you train, and you learn the weights of the network such that the weights represent the amplitude and phase at every 3D position. So you don't like train a network and then infer anything with it. You just train the network, and then the weights are your solution to the inverse problem. I think it's a little bit tenuous to call this neural network. It's nonlinear optimization. But a lot like neural networks, we can write this like forward problem and solve for the 3D refractive index, but it's a nonlinear, non-convex algorithm. And so we can't guarantee that it will always come to the correct solution. And furthermore, we can't really say when it will work or when it won't work. It kind of like depends on the sample. We can just sort of show that heuristically. And we have a pretty good sense of that by now because we've been doing this for a while. The cool thing about that is that, like neural networks, it can solve for all kinds of things that we sort of like never thought were possible. And in this case, it's multiple scattering. So if you think about like, I'm modeling how light comes into the sample, and then if this is like one voxel of the amplitude or phase of the sample, then light can scatter over here, and then it can scatter over here, and then it could scatter over here. So that is multiple scattering. And basically, we can model multiple scattering through this network or through this forward model. And so we're putting this into an inverse problem. We have a chance to solve for multiple scattering information inside the sample. And this was super intriguing to us. So if you think about 3D refractive index, it's often called the scattering potential. So this is like scattering potential equation. It's basically just the 3D refractive index with some scaling factors here. So the 3D refractive index is the scattering potential because it deterministically, if you have the map of the 3D refractive index of the sample, then it deterministically describes how light scatters through the sample, from one side to the other. So you can predict exactly how light will scatter through the sample, in which case you can solve an inverse problem to invert the scattering and undo scattering effects digitally. So if we can measure 3D refractive index accurately with diffraction limited resolution in the full 3D volume, then we can computationally undo all scattering. And that's really exciting. And how far can we go? Basically, we're compute limited. So both like capture limited and compute limited. So like the more scattering effects you want to undo, so the more multiple scattering you have, the deeper you want to go, then the more compute you need to solve this, and the less likely your computation is actually going to be correct in the end. Because as you scatter more and more, the degrees of freedom for how light scatters increase exponentially with number of scattering, with like depths basically, because the number of scattering events. So we're not talking about imaging through like 2 centimeters of tissue. We're talking about like less than a millimeter. And we want to do transmission mode to start with. So we're just going to look at like small organisms. But these things can be pretty highly scattering. And largely what people have used in past is just use single scattering models, the Born approximation. It results in a really simple 3D transfer function, which is linear in complex field. And so it's very easy to solve the inverse problem. But now we're talking about the 3D sample as if it was like a series of 2D slices. Each slice has an amplitude and phase that it imposes. And then the light sort of like diffracts off one slice and then propagates to the next one, diffracts off the next one. So that's like the simple model. We use a simple model because we need it to be computationally efficient, because we need to run this thing hundreds of times within an iterative loop to solve the inverse problem. And so this is the one that is a good trade-off between accuracy and compute speed, so that we can actually solve real problems. So like, okay, here's a cell. This is just a single cell. It's not very highly scattering. And we're just illuminating it from different angles. The angles that it's illuminating at are like this spiraling outward. And what you see in the measured intensity is you see like stuff in focus is not going to rotate. Stuff above focus rotates one way. Stuff below focus rotates the other way. So the depth of information is there. But the cool thing I want you to see here is that if I just take the Fourier transform of these captured images as I'm changing the illumination angle, what I see in the Fourier space, so this is the Fourier transform of the captured intensity. We're not capturing phase, remember. It's these two weird circles that are like following the illumination. So my illumination angle is like the center of one of these circles. So what's going on here? What's going on is that what I measured is intensity, absolute value squared. So when I illuminate from different angles, I said that shifts things in Fourier space. So that's why one of the circles is shifting with the illumination. And then the second circle is just the conjugate circle because we measured intensity. In Fourier space, absolute value squared amounts to an autocorrelation. So you're going to see the autocorrelation of a shifted circle. And this is what it looks like. And this is a hallmark of single scattering. So the light staying within these two circles in Fourier space means that the light was only single scattering. It was not multiple scattered. And that tracks. This is just a single cell. It doesn't have a lot of multiple scattering. And so it's very weakly scattering. It has these clear two circles in Fourier space. And then when I do my 3D refractive index reconstruction, if I just use like my single scattering or Born approximation, I get a pretty good reconstruction. So this is just a central slice of a 3D volume that we reconstructed. And it's just so you can compare single to multiple scattering. And they look basically the same in this case because the sample actually was roughly single scattering. If I use a more scattering sample, like this embryo, so C. elegans embryo, it looks more like speckle here in the raw image. These are just off-axis raw, illuminated raw images. And so now you see, I can see the two circles, but there's a lot of stuff outside of the two circles. And that can only get there by multiple scattering. So there's some multiple scattering in this sample for sure. And now you start to see the multiple scattering reconstruction pull away from the single scattering one. It keeps a lot more low spatial frequency information. It has a lot more contrast. And the numbers here should be much more accurate than here. And you get kind of like a high pass filtered version of it in the single scattering model. And if you go to even higher scattering, then you get even specklier raw images. You almost lose the two circles completely, and then you see a big difference between the single and multiple scattering reconstruction. So now we can get a much better reconstruction with these multiple scattering methods and really pick up on a lot more fine details that you just couldn't see in the single scattering model because it wasn't accounting for all the multiple scattering that's going on within the sample. And that is just like a tiny little subsection of this gigantic 15 gigavoxel quantitative refractive index map reconstruction. I'm just showing you the central slice of this worm, and this is a refractive index map inside the worm. So if you just tried to image this with a regular microscope, everything would be blurry because of the sample-induced scattering, because it has all these little balls of refractive index contrast. This is one end of the worm, and I'm just going to show a couple of different depths so that you can get a sense for the 3D information that's there. Okay, so I think this like technique is really cool. I'm so excited about like reducing multiple scattering. And Chateau was a postdoc in my group working on this. So he spent a lot of time on this. And one thing he went after was embryos. So different embryos have different amounts of scattering, but the lipids in the embryo make them scatter even more. And so like mouse embryos were relatively easy. C. elegans are getting more challenging. Fruit fly embryo was a good challenge. Like this looks like just total speckle, right? And if you look at some literature, you see like even confocal microscopy doesn't do a good job of imaging into a fruit fly embryo because it's just too highly multiple scattering. So that's what Chateau went after. He sort of got it got it fixed. So this is our 3D reconstruction. And you can see like in the center of this thing, there's a lot of hazy garbage because it just can't solve for that much multiple scattering in this particular case. Chatoa started his own lab at UT Austin since then, and he has taken some beautiful results. He basically just used a slightly longer wavelength to fix the problem, but also a few other really nice innovations. They're taking beautiful pictures, and I'll just leave that to him. Okay, so I still have 10 minutes, and I want to get into what I always get with biologists is like, oh, that's nice, but I don't do label-free methods. I always use fluorescence. I want to do functional stuff. And fair enough. Quantitative phase is becoming more and more popular because it's having more and more capabilities, but it's still fundamentally kind of like structural information about your sample. And fluorescence is where you're going to get functional information. And so we want to look at both. So like, can we just do this for fluorescence microscopy? The answer is no. Like if you illuminate a fluorophore from different angles, it doesn't care. It's just going to light up isotropically from wherever it is. And so like illumination angle patterning is not useful. But this illumination angle patterning is very analogous mathematically to structured illumination microscopy. And so actually like it's already been done in structured illumination microscopy. You illuminate with illumination patterns that are high spatial frequency, which is like illuminating from high angles of illumination. And that shifts things in Fourier space and captures different parts of the Fourier space. There's some cool work on speckle sim where you can illuminate your sample with a bunch of different random speckle patterns. And that will shift things around in Fourier space in a random way, but you can disentangle it computationally and solve for the super resolved image. So we did this. We generated our speckle with Scotch tape because it's fun. And we didn't go after a very high resolution. So we started with a 0.1 NA objective and we built it out 4x super resolution to 0.4. So it's not like beyond the diffraction limit of like half a wavelength. We had a couple different cameras so we could collect phase and fluorescence information and do the super resolution. This is what the raw data looks like. It's just a bunch of speckle patterns. And then you can resolve these are just beads that are both have like a phase component and a fluorescence, but you can get this 4x better resolution. Since it's 4x better in each dimension, you actually get 16 times higher content gain, and you have two contrasts because you have phase and fluorescence. Okay, so finally to the dynamic stuff. I talked about multiplexing for the LED array stuff. In this case, we have to think about like what can we do when this is too slow. So you have to take a whole bunch of images to reconstruct your super resolved image for structured illumination and for the LED array stuff that I talked about. And in our lab, we do all kinds of different, what I call multi-shot computational imaging methods, where you take a bunch of images and then you computationally reconstruct your final image from it. And if your sample is moving while you're taking that bunch of images, well, that's not good because then basically your sample is changing in time. So like, if I take 10 images to reconstruct a super resolved structured illumination image, then if each image is different because the sample was different at each time point, then I'm not going to get a good result, right? Like I'm just going to get a motion blurred result, and it might be worse than not doing super resolution at all. So now we need to like try to account for these object dynamics. So X is the object that we're trying to solve for, and now we need to solve for X of t. So that's a problem, right? Because we are trying to solve for the super resolved image, not for like how the sample is moving. And so we would like to solve for both. And the reason why we have a chance at this is because we're looking at samples that are relatively like smoothly moving or slowly moving. Oh, sorry. I don't know what happened here. Yeah, so we did this with speckle structured illumination. You take a single illumination pattern, we'll pre-calibrate what the illumination is, but it's some like low resolution speckle pattern. And rather than taking a whole bunch of images with different speckle illumination patterns, which is hard to achieve because you have to design the hardware to change the illumination pattern in time, we're just going to rely on the sample moving. So the sample is moving in some unknown way across the speckle field. And so different parts of the sample will see different speckle illuminations as it's moving. So it makes sense that each different part of the sample sees these different illuminations. So it's a lot like I had done speckle structured illumination. and I can get like this set of data set with the different speckles at each different part of the sample just by having the sample move. But now I want to solve for the super resolved dynamic scene over time. So I also want to solve for the motion. So I'm trying to solve for more things than I measured. And the reason I can do that is because of the smoothness in the motion. So like this worm is a great example. If I look at different frames of this video, they're all really similar. Things are just moving a little bit over time between frames. So we can model that really nicely with these MLP, multi-layer perceptrons. These are implicit neural networks. They're a really hot topic right now in computer vision, being used to represent all kinds of crazy things. In this case, we're using them very specific way. So they're coordinate-based networks. So you put in a coordinate, it spits out, in this case, it's a motion network. So you put in a coordinate of space and time, and it spits out how the motion varied over time. So basically, like, this one's going to model how the scene or like the sample is moving in time. And this scene MLP is going to model the super resolved image at a given time. So we treat the video as like a scene at a time t, and then a bunch of maps of how things are moving over time. So this is like a nice like sparse representation, right? Like these motion maps should be very sparse if the sample is moving in smooth ways. And so it means that we have a chance to solve this. We're not having to solve for, like n times more things than we measured. Okay, so you put all of this into a big like optimization function. You have some loss function to describe like how you want, you go through a forward model and then you predict some measurements and see how they're different from the measurements you actually got. And we can solve for quantitative phase. This is just simulation for quantitative phase, but showing this like reconstructive phase looks pretty good even for reconstructing a video. Here's some experiments. This is just rigid body motion. So the sample is just moving laterally pretty much in a linear line. So kind of boring, but we just wanted to verify that we can get the super resolution from it. And indeed, we can resolve these beads where in the bright field deconvolved image we cannot. This was a really nice experiment with a commercial structured illumination microscope. So this is sinusoidal structured illumination. And if you just look at the wide field image, you can't resolve these beads. But if you do sim, you can resolve all of these beads. So then what they did was they induced motion in the sample by shaking the table and taking a data set. So when you shake the table and take a data set, you get motion blur and you can no longer resolve the beads. But from the same shaken table data set, our neural space-time model with these neural networks can actually resolve all of these different beads. Here's some more biological samples, and you can see how things are moving over time during the time in which we captured a single data set for the super resolution structured illumination microscopy. Here's a 3D, it was a 3D sim. So over 3D, you have to take more images to cover 3 dimensions. And so things move even more. And I think it's really nice to like see all the little motions that are happening of all these tiny pieces that would otherwise be just blurred out in the final result. All right, so that is all that I have. I want to thank my students who did all of this work, our collaborators and my anti-collaborators who are downstairs yelling at their dad. I'm happy to take any questions. Oh, one last thing is that I want to plug our Micromanager. This is an open source software that Henry and my group wrote, and it's basically Micromanager, but you can do it all in Python, which means you can access all of the machine learning and Python-based tools for image processing. It's just convenient.
Thank you so much, Laura. That was insane. The images, the phase images are notoriously difficult to segment, and what you've achieved is outstanding. Thank you so much for sharing that with us today. Is there any questions? I can't see any questions for the moment. I'm just going to start then. We're all here, mostly biologists. How easy would it be for us to implement a system like yours when we're not physicists?
Yeah, great question. So I think a lot about this. I have a whole talk on like basically like reproducibility is like a function of how like robust your system is to like bad calibration. So I have a whole talk on like algorithmic self-calibration. So like the LED array stuff we've been working on for a very long time. We've designed, so this is our startup company sells these LED arrays, and they have little adapters that can click into your condenser unit. So very easy to get that up and running. You do need to like calibrate the LEDs. So like if you say it's at 45 degrees, it better be actually at 45 degrees. And in fact, the angles can sometimes be off just because like if your sample is floating in water and the water surface is not flat, that can cause a refraction error, which will change the angle. So this algorithmic self-calibration idea is that I showed you that the Fourier transforms have these circles, and you can fit to those circles and basically like calibrate the angles from the raw data itself. So you take like 5% more data, but you can solve for the angles as well as solve the whole inverse problem for the image. And then you don't have to worry about like us installing it wrong or like having it poorly calibrated. So that is super useful. It just takes a little bit of extra compute. So if you can physically calibrate it, it's better. So I think like the LED array stuff, certainly like, so what we found is like DPC, this differential phase contrast. So you don't get any super resolution, but you get quantitative phase. That is extremely robust. You can like install the LED array completely wrong and it'll still give you a pretty good result. But the Fourier tychography, like super resolution, you need to have some sort of calibration step, either physically or with this algorithmic stuff, which just takes longer compute. But you can get it going. Like we've had biologists get it going many times in past, and we're very happy to help people if they want to. The structure illumination stuff that I showed at the end with the dynamic samples is totally new, and like it just fails for weird reasons on like I don't know if somebody could get that up and running easily without some expertise in like tweaking the hyperparameters of the neural networks, which like I couldn't do, but my students can do. So I don't actually have a good sense of how plug and play that is, but I wouldn't recommend trying that on your own without like talking to us first. But the LED array stuff certainly is getting
I mean, at least just getting more
robust.
information out of all the phase contrast is amazing, because it's so hard to segment, to do automated segmenting, and so yeah, just being able to get all this information is would be fantastic. We've got
And I should say the LED array stuff is like there's a couple companies commercializing related things. Zeiss's new scanning microscope allegedly is going to have this essentially in it.
Okay. We've got a few comments, a few questions. So Samuel is asking, in cryo-electron tomography, when samples are thick and hence have more scattering, I believe that would decrease the quality of reconstruction. I'm just wondering if this would be helpful in such a case.
Oh, yes. So we have a project doing this for electron tomography, not cryo-electron tomography. Let me just show this. This is for like material science type electron tomography. So they want to look at, so this is like individual atom resolution across a pretty thick amorphous sample with a lot of multiple scattering. So atoms are extremely highly scattering. Like it's like having a very high refractive index contrast. In fact, like the refractive index map is analogous to like the atomic potential when you go to electron tomography. And so they're actually very highly multiple scattering when you're just looking at atoms. But the goals are different because they care mostly about dose. Like that's really the limiting factor. So this is going after low dose. So this is simulation. We don't have the experiments done yet. I'm like just waiting for the day when we can do this in experiment. But this is like metal samples and stuff. Like cryo-electron tomography is usually for biological samples. And I would love to get into that area. But largely like, so our collaborator on this material science stuff is like, the biology stuff is like really interesting, but they don't really have multiple scattering. So like, I think the idea is that like biological samples are relatively weakly scattering. So I think it would be like less scattering to look at cryo-EM. But I mean like that this method, like this result is exactly the same method. It's just putting in electron tomography data rather than optical data. So it's interesting, and like love to talk more if somebody wants to try something.
Cool, thank you. So Luke is asking, so amazing stuff and great talk. Aside from fluorescence, have you thought about how you could harness this 3D imaging technology to address functional biological questions?
So I'm not a biologist, and roughly the answer is no. I don't know biology very well. I have bioengineering students, and we work with biologists. We do a lot of stuff in neuroscience is the closest that where like we're actually getting into the science of like doing the neuroscience, but that's like still absolutely with and relying on collaborators. So like no, we rely on collaborators to like know the problems that you can possibly solve with this. Like this structure illumination stuff is with some people in molecular and cell biology who have ideas of like, oh, we can look at if this is a mitochondria branch or branching, or if it's actually just moving over time. Things like that are not my area of expertise. We're very much the technology developers. We're already having to put together skills in optics and machine learning, so we can't also be experts in biology.
No. That wouldn't be the expectation. Thank you. So we've got another question from Kit Curry. So his lab works on zebrafish. So speed seems to be an issue in many of the hardware setup that you beautifully illustrated. So a thick dynamic sample like the zebrafish larvae may not be optimal. Can you comment on current limitation for sample depth in dynamic imaging settings?
Yeah, I'm like super excited. So this stuff I showed at the end with the like the motion models with the neural networks, it's extremely powerful. So we've actually done it for the Fourier tychography, the super resolution with the LED array, and it works great. We've also done it for the electron tomography problem. In that case, it's the changes in time are carbon contamination, and it works great for that. And so I'm like super excited to also apply it to this like 3D refractive index mapping and see if it works there, because there's a chance you could then like basically get a video at the frame rate of like your data capture. So if you take 300 images to reconstruct one frame, you can reconstruct actually a video with 300 frames from it, which seems crazy, but this is like the power of what you can do it if these models work well. And these models work well if your motion is relatively like smooth, which is kind of hard to describe, but like if it's modelable by these models, then you can get away with potentially getting back all of the lost temporal resolution, which is like pretty incredible to me and exciting. But like it's one of these neural network things where like you have to try it to see if it actually is going to work. And it's not so easy to set them up. Like these are pretty large neural networks in 3D. You're going to run out of compute, and so there's still lots of computational problems to be worked out to even try it. But I'm excited. Like I think it could potentially work for all kinds of these different problems to get you to like being able to do fast stuff. Like I know exactly what this person's talking about. Like if I could make a video of like a zebrafish embryo growing in real time, that would be so cool.
So do you need to tailor the neural network for each type of samples, or do you have a one size fits all once it's optimized?
Yeah, so it's very ad hoc right now. Yes, you do a new neural network for each type of sample. They might be really similar, but the neural networks also are like hard, they're very opaque, they're hard to understand like what works and what doesn't work. So like it's not like, oh, I have this insight, I should change this and it will work better in this way.
Black magic.
There's a lot of like just try it and see what works type of stuff, which is sad for academics. But, you know, I can't deny that these things are powerful. So, and maybe someday we'll figure out better what's exactly going on inside them. So we have some insights on this kind of stuff, and machine learning is moving very fast. There's papers coming out all the time about like understanding why and how these things work. So I have hope that someday it could get better.
Cool. Well, thank you so much. I think that's all for the questions. Thank you so much for your time and explaining physics so easily and so beautifully. That was an amazing talk, and hopefully we can talk to you in the future.
Yeah, thanks. It was fun. Feel free to contact me if anyone has questions or thoughts.
We will do. Thank you so much. Bye.
Great. Bye.